Hello everybody, in this lecture we will be solving 1996 IMO problem number 2. Here's a view of this problem. In triangle ABC, we are given a point P which satisfies this condition. So let's have a sketch here. So we have our triangle ABC and P is, I don't know, maybe somewhere here. That's the point P, such that APB, so let's draw it, APB, so this angle minus ACB, okay, and then APC minus ABC. So those angles, I don't want to put any decorations on the picture yet, but then we are also given points D and E as the incenters of triangle APB. So the triangle APB, the angle bisector will be probably somewhere here. Oops, yeah, here. So that's the point D, and then E is the incenter of triangle APC. So somewhere, I guess here, that's the point E. Then we are told that we need to show AP, BD, and CE, they all meet. So basically these angle bisectors, so let's say that this one meets at X, and the other one, obviously these are angle bisectors, so this thing is equal to that. And let's call this one as, say, Y. So we need to show that basically X and Y are the same points. Let me use the angle bisector theorem on triangle ABP. That would imply that AX to XP is equal to AB to BP. In a similar way, angle bisector theorem on triangle APC would tell us that AY to YP is equal to AC to PC. So combining these two results, so basically to show that, so that what we need to show is that X and Y are equivalent points, if and only if AB over BP is equal to AC over PC, basically. And so we need to make the left hand sides equal, suggesting that the right hand side, so this is the condition that we need to prove, right? So we need to basically show this. If we can show that, that would immediately imply that X and Y are actually the same point, suggesting that these three lines AP, BD, and CE concur at the same point. Okay, from here you can come up with quite a different ideas for proving the result. I'll provide you with two. If I have time, I would like to show three different proofs, all synthetic. And in the next video, I would like to show you a projective proof, and if I have time, maybe a proof with inversion as well. This problem is a very nice problem. There is many proofs available on AOPS page as well. Even using inversion, quite a few different proofs are also mentioned. There's also some special construction related to the Apollonius circle as well. So this is a really nice question. But anyhow, here is one idea, one way to find this result. That's the result we need to show. Consider the isogonal line of AP. So this is a reflection across the angle bisector, so suggesting that this angle here is equal to this angle over here. So the angle bisector is somewhere in the middle, I guess. If I consider this line and I extend it all the way to the point Q, such that so let Q be such that, let me first write that BAP is equal to angle CAQ, and Q is exactly at the point such that AQ to AC is equal to AB to AP. So this would have implied the existence of spiral similarity, if you will. So Q is at this point. So basically I'm suggesting that, let me actually draw with some colors. So this triangle, I did Q such that this triangle here is similar to this triangle. Does everyone see why? Because we have these length ratios, and also we have that the top angles are equal. So for these, so this is side angle, side similarity here, and this point is really what I need. In fact, if I connect B and Q as well, so first of all we established that these two triangles are similar. So this implies, so these two conditions, this and this, would imply that triangle BAP is similar to triangle QAC. But like in any spiral similarity problem, spiral similarity situation, the spiral similarity comes with pairs of similar triangles, and it's not surprising to see that triangle PAC is also similar to triangle BAQ by the same reasoning. Why? Because, for instance, if BAP is equal to CAQ, these angles, this would also imply that angle BAQ is equal to angle CAP, because lines AP and AQ are symmetric with respect to the angle bisector. So that's a natural thing. And also using this construction, we get that this similarity also holds. Now we have two sets of similar triangles. Let's now exploit the length ratios. So from the first one, for instance, we would get that AB to PB is equal to AQ to CQ, and from the second one we will get that AC to PC is equal to AQ to BQ. Now we're almost done. So that's what we needed to show this thing. So we have the left hand side here matching the left hand side here, the left hand side on this matches the right hand side here. All we need to show is therefore the equivalence of these expressions to complete the proof, or in fact all we need to show is to show that CQ is actually equal to BQ. But that comes naturally from the given condition that we have not used yet, APB minus ACB. APB, so this is this angle, but notice that the way I created the point Q, that's equal to this angle over here. So those two green angles are equivalent angles, and as a result APB minus ACB will simply give you BCQ. So this would imply that the left hand side simply becomes BCQ, and in a similar way APC, so which is this angle, is equal to ABQ, and then ABQ minus ABC will give us CBQ. But this implies that triangle BQC is isosceles, implying further that, let me write it in this space, so implying further that BQ is in fact equal to CQ. So therefore, going all the way down, now I have that BQ is equal to CQ. For instance, in the right hand side we can just replace the BQ with CQ and boom. So these two expressions are equivalent, which implies the left hand side must be equivalent as well. But if the left hand sides match, then we are done, because we have earlier mentioned that if we can prove this equivalence, it would automatically imply that X and Y are actually the same point, and as a result the desired result follows, where AP, BD and CE, they are all concurrent points. Okay, here's an alternative way to conclude the proof. Still, let's assume that we did draw BX and CY, and we want to show that X and Y are actually the same point by showing this equivalence here. In this case, let me actually redraw the picture so that we have a good visual. So we have our triangle again, A, B, C, our point P, I don't know, somewhere here, and then our triangle here and here. And recall that all we need to show is that AB to BP is equal to AC to PC. AB to BP is equal to AC to PC. That's what we need to show. In this occasion, I would like to draw the circumcircles of triangle APB and APC. Okay, so that's APC. Oops, okay. So something like that, yeah. So I don't need that portion, and I don't need this for sure. Okay, so consider this as a circle. In a similar way, I will draw the circle. That's a much larger circle. But this is the circumcircle of APB. And now at this point, I make this crucial drawing. I will extend AP and I will draw the tangents to the two circles at C and the point B. Those tangents I claim should both meet at this at the line AP. The reason is that, notice that, so let's call this point as R, and let's assume for a moment that we don't know if this line go through AP. So let's assume that the tangent to the, let's call these circles as omega 1 and omega 2. So the tangent to circle omega 1 at B and the tangent to circle omega 2 at C, let's assume that they meet at this point R. Yeah, let's do some angle chasing here. Angle APB is in fact equal to 180 degrees minus angle ABR. I hope you guys can see that, because the BR is tangent to circle omega 1 at B, so ABR is subtending this arc AB, minor arc AB, and APB is subtending the major arc AB, so therefore they are supplementary angles. And in a similar way, angle APC is equal to 180 degrees minus angle ACR. Now we can go back to the condition of the problem. So the given problem, so what is given to us is that angle APB minus, I think it was angle ABC, is equal to angle APC minus angle ACB. Oops, sorry for that. Angle ACB. Now we can replace APB and APC with these two expressions here. So therefore this is equivalent. So this is given that 180 minus angle ABR minus, we still have this one, angle ABC is equal to 180 degrees minus angle ACR minus angle ACB. The 180 degrees cancel out. I will move this ACR to the left hand side and the ABR to the right hand side. So we have an equivalent representation. ACR minus angle ABC is equal to angle ABR minus ACB. So ACR minus APC. I think I wrote the given condition wrong. Let me check the given condition, because APB minus ACB. APB. Oh shoot, sorry. Okay. So this I did this a typo here. Let me correct my mistake. So let me just so the given condition is not minus ABC, but it is minus ACB. ACB here, and this one is minus ABC. Sorry for that. So this is ABC. So this one is also ACB, and this one is ABC, and this one is ACB, and this one is ABC. Okay, so ACR minus ACB will simply give us BCR. So on the left hand side we have angle BCR is equal to angle on the right hand side ABR minus ABC will give us CBR. So this implies that triangle BRC is isosceles, and as a result, this implies that BR is equal to CR. But now I can simply square both sides. So squaring both sides would give me BR square is equal to CR square. But BR square is just the power of point R with respect to circle omega 1, and the right hand side, so this one is just the power of the point R with respect to omega 2. As a result, R lies on R has equal powers with respect to both of these circles, so it must lie on the radical axis of these circles, but the radical axis of these circles is the line AP, so these 3 points will meet at the point R. And now I can conclude very easily to achieve this result. For instance, applying this power of a point argument, for instance, the power of point R with respect to the first circle will give us RB square is equal to RP times RA, implying, if I write it carefully, that should give me RP over RB is equal to RB over RA, but this combined with the fact that angle BRP is equal to ARB, angle ARB, so this would imply simply that triangle, so triangle RPB is similar to triangle RBA. In a similar way, if you apply power of a point R with respect to the second circle, RC square is equal to RP times RA, implying that RP over RC is equal to RC over RA. Again, we have from this and the fact that one angle is the same, so side angle side, we get the triangle RPC is similar to triangle RCA. And now finally we have using these two similarity conditions, for instance, the one which is useful for me, I believe, is this one, RB over PB from the first one is equal to RA over BA, and in a similar way C from the second one, RC over PC is equal to RA over CA. So all we need to show now is that, well, we already know actually that RB is equal to RC because we already proved that R is on the radical axis, it has equal powers, so RB and RC are equivalent here. RB and RC are equivalent. Now if I just simply rearrange these two so carefully, so for instance, if I just change place for these two, I'll get that RB over RA is equal to PB over BA, and for this one the same thing. If I just exchange these two, I'll get RC over PC is equal to RC over RA is equal to PC over CA, and boom. So we already have shown that these two are equal, the denominators are equal, so therefore the left hand sides are equal, implying that the right hand sides would be equal as well. So we have just proved that PB over BA is equal to PC over CA, and that's exactly what we needed to show. So this implies that the points, again, X and Y coincide, and as a result these three line segments, namely AP, BD, and CE, they meet at the same point, and that solves the problem. Hope to see you in our next video.